Okay, so in this video, I want to look at two more polar shapes, I guess, or polar things that we should know about. And I'm trying to avoid the word function because it's going to be our first equation that's not going to be a function, and that's a lemniscate. And notice, how do I know it's not a function? It's because it's r squared. And so remember, the only simple test, the only thing we need for a function to exist in the world of polars, is have an r. But as soon as you have an r squared, you do not have a function. Now, certainly I could introduce the square root and come up with two functions. R equals positive square root of a sine 2 theta, and r equals negative square root of a sine 2 theta. But together, collectively, r squared, it forms a shape that is not a function. And so if a is positive, and you might think, well, how could a ever be negative? It can, and I'll explain in a second. But if a is positive, then there's going to be one of two shapes. And so, again, we're just focusing on sine. We're just focusing on cosine. So if a is positive, then r squared equals a sine of 2 theta. It's only going to be 2 theta. So then it's going to form this particular shape. Well, a lot of times we think of 2 theta as a polar rose with 4 petals, which you'd be right. But now, if I only want r squared, and when r squared is a and a is positive, then you're going to only get the 2 petals that exist along the 45. So let's see, I just draw this petal, and I draw this petal, and that's it. A lemniscate makes a figure 8. I like to think about that. Okay, now how wide or how long are these petals here? It's a distance of the square root of a. And if you're thinking about, well, where did the other 2 petals go? So there are times when sine is a negative output. Right? Half the time sine's positive, half the time sine's negative. And if sine is negative and a is a positive coefficient, you're going to get r squared is equal to a negative value. It's imaginary. So the other 2 petals don't exist. They're imaginary. And all of a sudden, if you make a negative and then sine outputs a negative number, the product of those 2 now become positive, and that does work. So if a is negative, I thought I picked a different color. That's okay. If a is negative, then you get the 2 petals that would have been on this particular 45-degree angle. So, and notice I'm not really drawing on like a function, because it's not a function. It's just these 2 petals. And again, the petal length is equal to the square root of a, and then the same thing down there. Now, if we're on a cosine graph, so same idea, cosine, if cosine is positive, then the 2 of the 4 petals that we would see would be along the x-axis. So I'll pick another color here, maybe this nice orange. So you get a loop here, and you get a loop here. And again, the length of that is the square root of a. So this is if a is positive. So this would be r squared equals a cosine. And then if a is negative, we're going to get the other 2 that are hidden right now, that are imaginary. But if you let a be negative, then when cosine is negative, the 2 negatives will become a positive product. So you get these 2. So, and again, that distance there is root a. So, putting them all together, you would just be like r equaled that particular polar rose. But r squared means that you only get half of it, so to speak. Okay, so when it asks us to sketch the following, and I probably should have pointed out too that it's always going to be 2 theta. We're not going to deviate that. I mean, there are other graphs out there, like if you had 4 theta or 3 theta, you could make similar graphs. But I just want to know about just the 2 theta to get the lemniscates. So I know it's a lemniscate because it's r squared and there's a 2 theta. So since 16 is positive, and it's a sine function, it's going to be on the 45-degree angle marking, right? So positive. And I would go out the square root of 16, which is 4. So then, since it's not a function, I don't have to put a start or arrow as the direction, 1, 2, 3, 4, because it's not a function. So it's not going to graph the same way that we would normally think our roses would graph. 1, 2, 3, 4. And part of that's because if you think about the sine graph, sine's positive for a while, then it's negative for a while, then it's positive for a while, then it's negative for a while. So it would be a discontinuous equation to say the least, because you're only getting half of the domain there. Okay, but that's it. And as long as it clearly marks that is 4, comma, and then it is pi over 4 or 45 degrees, because when you put 45 in times 2, 2 times 45 is 90. So the sine of 90, that's the maximum that could get. Okay. Now, next one, r squared equals -9 cosine. So it definitely is a lemniscate, right? R squared, and it's cosine. So it's either going to be on the x-axis or the y-axis. Since it's negative, we go along the y, and we go out 3. That's the square root of 9. 1, 2, 3. 1, 2, 3. So we're on this axis, 3 and 3, and we just make a figure 8. I was gonna say a figure 8 figure, and I'm like, well, that's kind of redundant. Let's make that maybe just a little thicker, just so it shows up a little bit more clearly on our graph. As long as the endpoints are labeled, like that's a 3, and this is a 3, and you could call that 390, because at 90 times 2 is 90 times 2 is 180. Cosine of 180 is -1, and then -1 times -9 gives us a positive 9 value, the square root of it being 3. And the same thing, you can label this one, or as long as it's labeled along the grid, you're okay. Okay, and then let's look at the next one. Again, C and D are both lemniscates. How do I know they're lemniscates? Because there's an r squared, and then there's a 2 theta, an r squared and a 2 theta. So cosine being positive 36, so I'm going to go along this axis, and I'm going to go out 6 units, because that's the square root of 36. So 1, 2, 3, 4, 5, 6, and again make my figure 8. So it's the 2 real petals of that rose. 1, 2, 3, 4, 5, 6. The imaginary ones are hidden, and we could observe them if we made that a negative, and then we would see, that there'd be one here, it's imaginary, and one here, it's imaginary. Okay. The last example, when sine is negative, when the coefficient in front of sine is negative, then we are on the negative 45-degree angle marking. And we go out the square root of 25, which is 5. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. So we go ahead and mark our figure 8, so to speak. So that is, again, it is not a function, right? A lemniscate is not a function because it's r squared. And we're going to look at one more non-function, and that's within our lines. Now, we've seen vertical and horizontal on the very first day when we were translating, like, x equals 5. And we know that x is our cosine theta, and we could just divide the cosine theta across. So r equals 5 over cosine theta, like that, or secant theta. So we've seen this before, and same thing with the horizontal line. The second kind of line is an oblique line through the pole, and that's where they just say, hey, theta is some angle. And if they just say graph theta is pi over 3, then you're just going to draw a line that has an angle that goes through pi over 3. And since it's not written as r equals, it's not going to be a function either. Okay, so let's look at a couple of examples here. So it says find the equation of the vertical line that passes through the point 5, 180. So if I were to graph 5, 180, that's right there. There's 5, 180. And so the vertical line that goes through there, so I know that vertical line is 5 units away from the origin, but it's 5 units to the left. So I would say that's r is equal to -5 secant of theta. Or if you preferred cosine, you could say r equals -5 divided by cosine of theta. Same, no, they're both fine. Second question, find the polar equation of the horizontal line that passes through the point 4, 45 degrees. So 4, 45 degrees is right there, a radius of 4. So that's 4, 45 degrees. Now I want the horizontal line that goes through there. Be really careful because that line is not 4 units away, right? It's actually 2√2 units away from that, I guess from the pole or from the horizontal line. So since that's 2√2 units away, and how did I get that? I just drew a 45, 45, 90 triangle. So then I could say that r is equal to 2√2 cosecant of theta. Because again, it's a horizontal line, so I would normally think about it as like y equals 2√2, and then every time you have a y, you can replace with r sine of theta, and then divide that sine underneath, and that's how we're getting cosecant of theta. Okay. So then it says find the polar equation of the oblique line that passes through the point -230 and the pole. So, okay, so -230, so 30 degrees, but -2 is back here. So there's -230, and it says give me the oblique line. So actually give me the line that goes through that point and the pole, which is the origin. So right there. So there's actually many ways that we can express this line. One way is we could just say theta equals 30 degrees, or pi over 6. If you wanted to give radians, that's fine. But see, the thing is, you could also say 210, right? Because going 210 will still land you on that same slope, which is 7 pi over 6. You could also say -150 degrees, or -5 pi over 6, right? So like it's not unique, but because it's not r equals, it's also not a function. And so that's really the second kind of non-example, right? One is a lemniscate because it's r squared, and the other one is an oblique line through the pole. And so that would be like theta equals. Now we've had other lines that are functions, like horizontal and vertical, but an oblique line through the pole will not be a function.